set has measure 0. On the other hand, if you just think that any ternary decimal you can map in a sort of one-to-one way by just replacing a 2 with a 1, and by just noting then any value of x can be written in binary with 1s and 0s, you can immediately see that the Cantor set is also an uncountable set. So I think Cantor originally sort of came up with this as just showing you illustratively an example of a set which is uncountable, which has measure 0 on the real line. But at the time it was just a curiosity, but the more interesting thing perhaps now is it's the invariant, it can be shown to be the invariant set of this quadratic map. Okay. Now, so we consider, so the idea of a symbolic or a symbol sequence is to think of of some sort of partition of this invariant set, and a natural partition would be to consider all the points sort of in this half of the invariant set, use this symbol, and this is an orange. By the way, I originally had apples and oranges, because apples and oranges are really very different. You should never mix apples and oranges. But I was then very surprised to find at breakfast, George can tell me this, I got totally confused, because when I tried to find orange juice, there was something, what was it called, apfel juice or something, and then next to it there was another one which was apple something, sin juice. Is that right? So I decided
Appleseed is orange.
Yeah. Well, this is it. I got different types of apple juice, so there's no, where's the orange juice? I had to go off.
Yeah, but that's Chinese apple.
This is it.
Yes, that's Chinese apple. Yeah.
So I decided that obviously in Sweden apples and oranges aren't so different. So I decided not to use an apple here just in case it confuses.
He's completely right.
Huh?
Appleseed comes from
Chinese
apple. It means it linguistically.
Is it Chinese apple? Blame the Chinese.
But in Spanish it means apple without juice.
Anyway, so the point being, there's obviously no point in using apples here because they're all the same thing. So I've just used an upside down orange instead. So the point is, these are just symbols, okay, and they represent, they denote different this partition, if you like, of the Cantor set. So we can. So what we do is we consider another way of representing a point in the invariant set. So x is a point in the Cantor set, and phi is a kind of mapping to a symbol sequence. So each of these A0, A1s are either up oranges or down oranges, and the nth symbol is an up orange if the nth iterate of this quadratic logistic map applied to x. So you map, so you're down in the Cantor set, and this f, you're applying it n times, so it's mapping you around. After you've done it n times, you can ask, are you in the up orange bit of the set or in the down orange? So if you're in the up orange, then that symbol is up orange. And if after n iterates you're in the down orange, the symbol is down orange. So, yeah, actually this seems to be a bit missing here. So if x was say my point 220 internally, so that's a point dot dot dot, these are 2s and 0s. Then under this mapping, the symbol sequence, at least for the first 3 elements of the symbol sequence, would be down orange, up orange. Well, okay. Well, let me just use 0 and 1 now instead of up orange and down orange. So you know, we have this duality. The point is, we have this duality. We can either think of the state x as a point in a particular point in the invariant set, or we can describe x by essentially you could think of it as a time sequence of symbols. So 1, 1, 0, this is now 1, this is the 1 symbol, instead of the down orange, and 0 is is instead of the up orange. So these are two sort of equivalent ways of describing the system, both the state as a point, as a particular state, and the sort of time sequence under repeated iterations of the dynamical logistic map of where, if you like, that state goes to with respect to this kind of coarse binary partition of the invariant set. And in fact, yeah, in fact, in symbol space, the quadratic logistic map F actually corresponds to a left shift. So I'm calling it, if so, okay, let's just see if there's any more. I've forgotten the base. So suppose I had a state and its symbol sequence was that, and then I operate on that state, little x, with f, my little f. The equivalent mapping in symbol space is just to shift the sequence, or if you like, if I had a pointer there, the pointer would go to there. So you could either think of the whole system being shifted and then dropping that one, so you're just left with that 101s. Okay? Or if you like, had a pointer which just moves you along. So this is this idea that the nonlinear dynamics in symbol space is actually just a rather simple kind of shift operation with respect to that partition. So this is an important sort of thing. I want to get over this kind of duality. There's this state space description and the symbol space description. The symbol space you can just think of, if you like, as a time sequence of the position of that state with respect to binary partition under the action of the nonlinear dynamics. And then you have the original nonlinear dynamics in state space, and then this corresponding operator, the shift operator in symbol space, and they're doing the same thing. And in fact, more generally, and this is what people, when they get into the mathematics of all this, talk about, is kind of homomorphisms between the original dynamical space and the symbol space. This could be for a one-dimensional system, but in fact it generalizes completely generally when you have, I would say, a multi-dimensional Cantor set, for example, some Cartesian product of Cantor sets, and then you have a kind of n-dimensional set of symbol sequences. And one way of thinking about this could be, you know, when you're describing n chaotic oscillators. So, I mean, there's a lot of work, for example, goes on in looking at coupling of these logistic maps. So instead of just having one logistic map, you might have several of them, and they're coupled together through these sort of coupling terms. And you can represent that through n, if you like, of these symbol sequences. Now, if the oscillators are completely unsynchronized, they're just kind of going on independently of each other, then obviously these symbol sequences will be uncorrelated. And one can think then of the effective dimension of the total attractor. If you think of this as a system with a sort of total attractor, then in the case where everything is unsynchronized, really you're just dealing with n independent attractors, and the dimension will just be the sum of the dimensions of the individual attractors. On the other hand, when those coupling terms are such, for example, as to bring the system into complete synchronization, and that is a very common feature of chaotic dynamics under circumstances, you can have complete synchronization, even though these time series of ones and zeros are completely non-periodic, the individual oscillators can synchronize. And then effectively you're just dealing with n copies of a single system. So the dimension of the system is then just the dimension of one of those oscillators. So in some sense you can think of coming into synchronization as being associated with a dynamically induced reduction in the dimension of the underlying total system attractor. Now, one point to notice is that